Alrighty, so in this video, I'm going to talk about energy stored in a capacitor. Well, I'm actually not going to talk about it quite yet. I'll overview it real briefly. Just this is the expression that we use when we want to determine the amount of energy that's stored in a capacitor. Okay, so it's just going to be 1/2 multiplied by the capacitance, and then multiplied by the voltage across the capacitor squared. Okay, so if the voltage across the capacitor is 0, then there's no energy stored in the capacitor. Okay. As that voltage increases, then we can see that the amount of energy stored in the capacitor increases quadratically, or as this voltage increases, then the energy increases by the voltage squared, or is proportional to the voltage squared. Okay, and so, but as you've probably recognized by now, I don't really like to just throw an equation out there and just expect you to use it. I like to derive it and show you where it comes from. And so where this expression actually comes from is that the energy stored in the capacitor can be determined by taking the integral from 0 to infinity of the voltage across the capacitor over time multiplied by the current through the capacitor over time. Okay, and so real easily we know VC of t, right? That's just our charging equation, which is our final voltage multiplied by 1 minus e to the minus t over RC, right? And so we can also really easily find IC of t, because IC of t is just C times dVC of t dt, which is C multiplied by the derivative of this VC of t. Okay, so if I want to find the derivative of this VC of t, I can do that real easily. IC of t is equal to C times, my derivative there is going to be, well, first of all, the 1 is just a constant, so the derivative is going to be 0. So 0 minus, and then I'm going to have my negative 1 over RC times e to the negative t over RC. That's my derivative. These two negatives make a plus. Oops, big eraser. These two negatives make a plus here. And then my c's cancel. And so what I'm left with for IC of t is just VCF over R multiplied by e to the minus t over RC. Okay, and so now to find this energy stored in my capacitor, all I have to do is multiply my VC of t up here by IC of t and take the integral. Okay, so let me go ahead and do that. EC is equal to the integral from 0 to infinity. For IC, it's VCF over R, e to the minus t over RC. Multiply by VCF times 1 minus e to the minus t over RC dt, all right? And so I can real easily just pull a VCF squared over R right out of there. And I'm left with e to the minus t over RC times 1 minus e to the minus t over RC dt. Okay? Let me go ahead and minimize some of this just so that I have more room. I guess I'll just minimize this stuff. Oops. Just minimize this stuff right here. So I'll move that there, and I'll keep going. And so if I factor this, I get VCF squared over R times the integral from 0 to infinity, e to the minus t over RC minus e to the minus 2t over RC dt. And when I go ahead and take this integral, I get VCF squared over R multiplied by the integral of the first term is just going to be negative RC times e to the negative t over RC minus the integral of the second term, which is going to be negative RC over 2 e to the minus 2t over RC. And then those are going to be evaluated from 0 to infinity. Okay, and then I obviously have a plus here because I have two minus signs. So let me just move on up here by copying this. Hopefully I didn't grab the arrow too. Oh, I did. Oh well. And then I'll put my little plus in here. And then what I'll do is I will go ahead and start, actually, I'll factor out an RC I can factor an RC out of both terms. And then what I get is minus e to the minus t over RC plus e to the minus 2t over RC from 0 to infinity. My r's cancel, and I'm left with c times VCF squared. You can kind of start seeing this thing take shape here. And I'm going to go ahead and start plugging in my bounds. Actually, I'll flip these two so that the plus one is here first. E to the minus 2t over RC minus e to the minus t over RC from 0 to infinity. Okay, so I'm going to go ahead and plug in bounds now. C VCF squared e to the minus 2 times infinity over RC minus e to the minus infinity over RC. Both of these terms go to 0 because any e to the minus infinity is obviously 1 over e to the infinity. That's basically 0. So these both go to 0. And then in my second, I have to plug in the zeros. So that's going to be e to the minus 0 over RC. Oh, you know what? I lost a half somewhere in here. Yeah, right here. This half I lost. So let me put that back in here. This is divided by 2. This is divided by 2. This is divided by 2, and now this term is also divided by 2. Sorry about that. And so now my last term that I have to plug a 0 into right here is another e to the 0 over RC. This was really 2 times 0, but it's still 0. And so what I get is this whole term goes to 1. This goes to 1. Or not the whole term, but the numerator here goes to 1. And so what I end up with is C VCF squared times 0 minus 0 minus 1 half minus 1. And so this term here is negative a half. The negative makes this whole thing 1 half. And so I get that EC is equal to 1 half times C VCF squared. All right. And that is the equation that we were looking for the energy stored in a capacitor. Okay, so I like to derive these equations, like to show you where they come from. In the next video, I'll go ahead and talk a little bit more about energy stored in a capacitor, and we'll just solve a quick example where we determine how much energy is stored in a charged capacitor.